G'day viewers. In this segment I'll talk about some of the future directions for HTTP. So we've covered all of the topics that I wanted to cover for HTTP, and you should have some appreciation for how the protocol works. But the web's not done, of course. It's going to continue to move on and pages will get more and more complex, and there'll always be the need to make the web faster over time. The question for us is, well, how's it going to happen? What's going to happen to the web protocols to make them perform more effectively than they already do? What I'd like to do in this segment is just have a very brief look at some of the work that's going on right now and some of the options. So since this is really work in progress, you'll have to look back later to see what's happened to the actual web protocols. One of the first things we can do is take a closer look at modern web pages. Now, over the past small number of years, some very good tools have been developed to help us understand what happens when you actually load a page in a browser. Recall we said it depended on all sorts of things. Well, this is an example of what's called a waterfall diagram. There are many tools that produce them. Support's built into popular browsers, such as Chrome, for instance. And this is some of the output which comes from a popular open source tool called Web Page Test. And if you just Google that, you'll be able to find out where you can run it on the web. This is a very complicated looking diagram. I'll go through it in a bit. But it is produced, it's a fraction of the waterfall diagram that's showing how http://coursera.org is loaded by Firefox, running over a network with 5 megabits per second of download speed, emulating cable, from Virginia recently. So all of those things matter. You change any one of those, you would end up with a different picture. Okay, anyhow, so what does this diagram mean? Well, here's time going across. Well, this is time. So really going across, you're looking at sequential activity. Going up and down, you're seeing parallel activity. These are all of the different web resources, and where they overlap, there is parallelism in the network. There's not a lot of overlapping yet. Things are always going to kind of follow this curve where they fall off like this, somewhat like a waterfall. Because you usually can't get the later resources until you've learned that you need them by fetching some of the earlier resources. Now the color coding here is fairly complicated. The key at the bottom tells you a little bit of what's going on. I don't claim to understand all of this diagram, but we'll still walk through it a bit. Let's look at the very beginning. So this is where we start at time 0. The first thing we do when we try and look up Coursera.org is this is the dark green code, so a DNS lookup. So we actually have to do a DNS lookup to find out the IP address for Coursera.org. Then there's orange, there's an initial connection, a TCP connection to it. And after the TCP connection, it's mostly green, so that means that we're spending most of the time waiting to get the first byte back from the server. So we set up the connection, then we have to send a request and wait for the server to send a response. So just like the TCP connection setup, there's at least a round trip time delay here. This whole event took 274 milliseconds, you can see here. And I can see here it actually returned to 302. Now I know just from looking up HTTP codes that that is a redirect. And so the answer to this, and on the real screen you can dig down more. The answer to this redirect would be that the server would be telling the browser to go and visit another URL. In this case, it's telling us to go here to switch over to HTTPS rather than HTTP to be secure. That's the little lock, and that we should visit www.coursera.org, that server. So Coursera.org was really a shorthand for this www.coursera.org. Okay, so now we want to go and visit this server. And there is a DNS lookup. Oh, by the way, you can see I'm skipping some of these ones, the GoDaddy ones and the DigCirc. This is a lot of other behavior related to HTTPS, I think, to verify or revalidate certificates online. This is just one of the other weird things which live in browsers. There are many, many strange things that live in browsers. I don't really understand it yet, so I'm not going to go into it. I'll just stick with the regular page load. So now we do another DNS lookup. This is all adding sequential time, and we have to make a connection there. Now there's a purple That's actually SSL negotiation. We haven't gotten to that yet, but you can see that the modern web is mixing in a lot of HTTPS, even when you try and get something with HTTP. So this was a really just like a connection setup to make sure everything was okay. And eventually there's some gap. I'm not sure why there's a gap, maybe because of other activity. It's very hard to know without having the browser tell you what was going on. There's probably not enough information here for us to do other than guess. There's a delay until the first byte, and then the first byte must come in. The reason you don't see that is that would maybe just be a tiny blue bar at the end, because maybe only a kilobyte of information was needed. At any rate, after this, you can see that later on, there is a little bit of first byte and content delivered for other things. We have a CSS resource, style sheets, and JavaScript resources. They come in. Oh, it looks like we needed another DNS and another TCP connection setup. That's because another domain's involved here. This would be maybe the CloudFront for Amazon hosting, this long URL. So once we've got the Coursera beginning, we then contact other Amazon servers or whoever is hosting the page to get it. So that's why we need more DNS and more connection setups. Then there's a little bit of waiting and content begins to come through. It looks like we maybe have just one connection here. And we're then sending We're then sending multiple different requests here, probably over the same connection. So we have some kind of persistent connections. And eventually we're getting up to speed. Something's beginning to use the network and we're seeing content come through. Now the loading process continues, and we would have to look a lot more carefully to know what's where. At all of the content that comes back to understand why it unfolds in this way. There's a blue line about here. This line here is the document complete line. This means we've actually gotten in everything that's needed in the initial page. Actually, the rendering of the initial page started back here. So our computer started to display it on the screen, but it could have changed and might need to be updated until at least the document was complete. After the document's complete, you might wonder what could possibly be going on. Well, scripts could be running on the page, which causes other information to be fetched, as well as the strange things that happen inside web browsers. For instance, I happen to know that this next one here, this is favicon.ico. This is just a little icon which is fetched by the browser to display in the bar the site in your URL bar. So it wasn't part of the page contents. And then there's a lot of other stuff which might be scripts or information being loaded by programs running in the page. And the page will continue to evolve. So as you can see, a web page load can be quite complicated. In fact, it's a lot more complicated than I've shown you. Here is the full picture for downloading the Coursera page using the same settings that I had before with this web page test tool. So you can see that there's actually a lot of activity here after the document complete. We're loading in probably a lot of pictures, looks like, and other things, and scripts. The whole web page itself is comprised, or at least everything we see here, which happens to make the page, is comprised of 23 requests. It's around 1 megabyte of data, and it takes 2.6 seconds to get to the end of it. When we don't have anything cached, it's actually shorter if you do a repeat load and you have some things cached. Moreover, this is actually not a terribly complicated web page. It's not unusual to see 50 requests or even 100 requests on many web pages. So as you can see, some of these modern web pages are really very complicated. There's a little bit more, just to look at the bottom bit of this graph. There is an indication of just how our CPU and bandwidth are used throughout this process. The bandwidth looks like something like this. So this actually means that for the first second or so, we're really not using the network bandwidth very much at all when you're setting up connections, different kinds of connections. So we're not using the network bandwidth to its fullest extent. It looks like for the next second, though, we're using nearly all of the network. That's really good. Actually, I'm a little surprised and skeptical that that's really the case, but that's what this line is showing us, that we're using the network. The CPU utilization also jumps around a bit. You can see the CPU is doing a little bit of stuff. Now, I wouldn't be surprised, sometime after the start rendering, you can see it sort of jumping up around here. That's because we started rendering, which is often a CPU-intensive operation, around here, and as the document was complete and we really needed to finish drawing it, more CPU's activity is spent. If you're interested in this, you can investigate some modern web pages yourself. It's really quite startling just to find out what's going on inside a web page. One thing that you will find is that, unfortunately, and this is what makes web performance a difficult topic, the waterfall diagram, which is showing us the details of what's going on, and hence the page load time, which is the end of the waterfall, depend on many different factors. In fact, you might be somewhat surprised to learn that the waterfall diagrams look very different for different browsers. Try it on some of the pages with just different browsers and you'll see. You would think if all of the browsers were implementing the same protocol, you might get roughly the same behavior. But they are very different because implementation strategies matter greatly in terms of achieving good browsing performance. They're also different, as I noted, between reviewing the page, a repeat view, and a first view. What I've shown you is the first view, and actually maybe a repeat view would make more sense for something like Coursera, where you've been there before. And you even find that, in fact, the page load time often depends on the local computational resources that you have available as well as the network. And the reason for this is that script execution and rendering both need to happen as well as network activity to be able to load and show the page. So wow, modern web pages are quite complicated. Hopefully just some of those figures gave you an appreciation for that, and you can look a little more yourself. The question that I just want to talk about briefly here is, what are we going to do looking ahead? Pages are only getting more complicated over time. Every year it seems that the size of pages, the number of components they include, get more and more complicated. And they're also getting not only larger, but more dynamic and more secure. So more programs are being run, and we're using HTTPS further, which complicates caching more. The question for us is really how we're going to design the network system here to reduce the page load time, or at least keep it as low as possible, because we know that's important for people to use the web. Well, no one really knows the answer here because this is ongoing research, but I'm going to briefly talk about a couple of options which seem really quite useful. The first option is really better use of the network. And if you like, you could think of this as just as HTTP 2.0. How can we revise HTTP beyond 1.1? What brilliant ideas are there which will make page load time better? And the second topic I'm going to talk about is actually a little different. Might get you thinking, and that's about coming up with better structures for the content. Because even though HTTP is a separate protocol than the content, it turns out the way the content is structured has a big impact on the page load time. And here I'll talk about some server extensions. Okay, let's dive into those two. Now, first of all, this protocol called SPDY, S-P-D-Y, pronounced Speedy. SPDY is an experimental protocol which is now being tested and deployed. It runs in browsers such as Chrome and Firefox. I think for modern versions of these browsers is actually the default protocol. So instead of HTTP 1.1, your browser will try and use the SPDY protocol to talk to servers. And if the servers also speak it, it will use that protocol. It's forming the basis of an ongoing effort that's just sort of getting everyone excited now to revise HTTP again. I said, if you recall, that it had been stable for really most of a decade. Well, now it's time to move it from 1.1 to 2.0 to try and improve performance. Well, exactly how can SPDY do that? SPDY has a set of features, each of which maybe helps somewhat. How effective these features are together or individually is a little up in the air because it depends a lot on the web pages, so people are gathering data. SPDY has features such as, just to pick something that's fairly easy to understand, compressed HTTP headers. The headers have gotten bigger over time. They didn't used to matter much. Now they're a lot longer. Compressing them can reduce the bandwidth and help. The biggest change for SPDY is this first one. It has multiplexed or parallel HTTP connections on a single TCP connection. Recall we saw parallel TCP connections with HTTP on them individually early on, and persistent connections replace that. In a persistent connection, you have one TCP connection and then sequential HTTP request responses. They might overlap a little bit for pipelining, but they're not all happening in parallel. With SPDY, the next step in the evolution is to perform these HTTP requests in parallel and to allow the client to change the relative priorities of the parallel downloads. This is so if a client has 3 requests outstanding, they can all come in at once, and the client can tell the server, hey, I think the second one is actually more important, so send that, try and send that first, and then send the rest. And it could change its mind later. Another feature which is very interesting for HTTP is what's called, is a very interesting extension of HTTP for SPDY, is what is called server push. Normally, the model is that a client requests a resource and the server simply responds with it. With server push, when a client requests a resource, the server may respond with that resource and also push other related resources, as in, here, have these too because I think you're going to need them and ask me for them in just a moment. It can be somewhat difficult to work out how to effectively do pushes because it interacts with caching. You might already have copies of some of these resources. So it's ongoing work to work out how to use some of these features. But nonetheless, I think the insight that I'm interested about here is really changing the structure of HTTP. This is probably what needs to happen to be able to improve the performance significantly. Okay, so that's all I'll say about SPDY, but you can read more about it on the web and look at it in your browsers. Let's turn to the server now and the mod page speed extension. Here the observation is that the way pages are written, the way they're structured, affects how long it takes to download them. In fact, if you're authoring web pages or developing web tools or websites, there are many books that you can buy here that tell you about best practices authors and developers should use so that their pages will load fast, using small pictures, putting bits first, trying to avoid blocking JavaScript, doing all of these different things and so forth. So far, if you're authoring the page and following a best practice, you're a person doing that. The idea here for mod page speed, or more generally for other approaches that are going on, for other projects that are going on, is to have the server implement these best practices and have it essentially rewrite, or you could think of it as compiling pages. So if you think of the page as really just a description of the structure of the content, the server can work out how to lay it out in the way so that it will load fastest. This is kind of what compilers do when they have programs and they optimize things, and we're probably better off leaving it to programs as soon as we work it out how to do it. Mod page speed is an extension that goes in the server which performs this rewriting or optimization task by restructuring your content, something that HTTP can't do by itself. I'll give you just a little more detail on mod page speed. It is an HTTP server extension, so it's part of a software module that's installed with your web server. Its purpose is to rewrite pages on the fly. So when you request a web resource, it will generate it, but then it might restructure it and change it before returning it to you. And it's going to try and give you a copy which will be structured so that it loads as quickly as possible. How does it do that? Well, with all of its rewrite rules. Here are just some examples of the rewrite rules to give you a sense of things that can happen. It can rewrite the page by minifying JavaScript programs. This means reducing them by throwing away unused bits of code that are in JavaScript files, by changing the JavaScript itself to replace long variable names with short variable names so that the JavaScript code is as compact as possible, so we're going to need few bytes to transfer it. That's one thing it could do. It could also flatten multiple levels of include. For instance, in style sheets, one style sheet can include another. And if you have several levels of includes, every time you get a style sheet, you just learn you have to go and fetch another resource to find out what the whole style sheet is. The server could fetch them all and inline them all together. This is what the flattening is. And these are really compiler techniques you can think of, various inlining techniques and so forth. The server might also resize the images to suit the client, depending on what client is asking. And actually, there are many, many more. It's difficult for me to explain some of these rules to you because they really depend on a lot of the ins and outs and very specific situations in the web, which people know about and would like to avoid. In fact, there are hundreds of specific rules. But more than the actual rules themselves, the reason I'm mentioning this is I think this approach of having the server rewrite your content and restructure it is a promising one. Okay, so now you know about a couple of directions for the future development of the web to speed up the page load experience. Check back much later to see what's actually happened with the web.